this footnote is not particularly going to be as long as the other footnotes. Because in this one, I just want to talk about F-Polynomials. Because during my 4 more Femboy Donuts footnote, I mentioned a type of donut, or type of Femboy Donut, which I called FT2E, FT2E var phi of F. And it's characterized by the atlas, well, S2, FS2, and the Cartesian product with itself, and some F-polynomial such that, phi F and correspondingly F are just 5F, and F itself, the domain of F, is within the underlying Femboy set, or the product of the underlying Femboy set with itself, so F2. And you guys already know the FS2 here, so it's a Femboy circle of dimension 2. So it's solid shell, and then this is an embedding also. Need to also state that phi of 0, so the roots of this F-polynomial lies within the boundary of our torus. So given FT2 and its boundary. So, alright, so when I talked about this, I told you guys that, oh well, since we don't have much time for this footnote, I'll just discuss what an F-polynomial is, this over here, this var phi, in a different lecture. And so, today's the day. So, what exactly is var phi? What is an F-polynomial? So, you guys already know what polynomials are. A polynomial is, well, it's an expression or a mathematical expression containing 1 or 2 or more variables. If it's just one variable, it's a monomial. It's in your basic algebra. So something like, say, x, or 1 plus x squared plus x cubed over 3 factorial plus x to the 4th over 4 factorial, ... This is a polynomial. In fact, this, I believe, is the Taylor series expansion of e to the x, our exponential function. So this is an example of a polynomial. Another example of a polynomial is something like x squared minus 36. So this is equivalent to x squared minus 6 squared, and then, difference of 2 squares, x plus 6, x minus 6. Another example of a polynomial is, I believe, sine x squared plus cosine of x, or e to the I e to the ix, which is squared, which is cosine x squared plus I sine x squared. So these are technically polynomials. I know this is I know these two are trigonometric functions, but these guys are polynomials nonetheless because they contain more than one variable, independent or dependent. So that's the basic concept of a polynomial, or rather polynomials in the different branches of mathematics. Now, what we want to do is construct an F-polynomial to just show you guys what it is. So, an F-polynomial or a Femboy polynomial is some abstract polynomial, something like a generating function that takes in femboys as inputs and gives you femboys as outputs. Okay, so in one context, if we think of both axes, or if we think of our space as a sort of, femboys, right? Cross more femboys. Take the function of a femboy, and then you would get a femboy as an output. So let's say we have the underlying femboy set, and then we take its Cartesian product. So that means we have an axis. You have an xy axis, and this is F and F. So take one input here, say x1, and then it would have a corresponding output, which is var phi of x1. So with an x1 output, we have a corresponding y value, you can say, or value in this f direction. So this, or rather, a line or curve, wherein this is a part of it, this curve would be described via a polynomial of x. So this would be f of x n, where we have a specific point x1 that is part of this curve or this graph. Topology would call it a curve because it's one dimensional and it's only a line. So these things are described by polynomials, and various polynomials give you various kinds of graphs. So polynomial of degree 1, as you've learned in algebra, gives you a straight line, a linear graph. A polynomial of degree 2 gives you a parabola, or parabola, something like that. And x cubed, or x with a degree 3, would give you something like this, I believe, a squiggly graph. But nonetheless, it either goes to minus infinity or positive infinity, or positive infinity, minus infinity, but it has some squiggly, wavy stuff inside. And I need you guys to notice that the more we sum, I want you guys to notice this expression. I want you guys to notice this expression over here. I gotta just hold it. I want you guys to notice this sum for n, x to the n over n factorial. I want you to notice this sum over here. This is a polynomial, technically a polynomial. But notice how, as we approach infinity, as we take the limit of this function as n approaches infinity, this approaches 0 over here. You notice that from your basic calculus. But, where was I? Okay, so notice how the more we sum up various versions of n, so plug in n and then add them up, notice how we sort of approach some function. So we can use polynomials over here, so regular polynomials of degree n, and take their sum to approximate a given function, like say x squared. And that, my students, is given or found, or well, functions are approximated via a thing called Taylor series. And the Taylor series is, it's a series, or rather, it's a sum of derivatives of a given function. And so we're given some boundary condition or some initial condition of the function. Let's say we're given f prime of 0. So we're given the derivative of the function at the point 0. So we're given a value for that. From there, we want to conclude what the other coefficients of our Taylor series is to find out what's the best approximation to our function. Because when we have a Taylor series, the most important thing, or the most important thing we focus on the Taylor series is not the function itself, but the coefficients that make up the function. The coefficients that are part of the Taylor series. So a Taylor series is given by this sum here. So n, given by n, and then I believe some x, f of x prime, f prime of x over, I believe, n factorial, and then x minus n to the n, I believe. You guys can search that up. So this term here gives us our coefficient, and so given that one, we have some neat approximation for a given function. So one example of our use of the Taylor series is by trying to approximate trigonometric functions. So functions such as cosine or sine. Let's say sine. We know that sine is an odd function, so that means its Taylor series, or the terms in its Taylor series, will fluctuate between positive and negative values. So if you'll notice, when you try to search for the Taylor series expansion, or the series expansion of sine, you'll notice that it's something that goes like 1 plus x over, or just 1 plus x. 1 plus x minus x to the x cubed over 3 factorial plus x to the 4th over 4 factorial minus x to the 5th over 5 factorial plus, and then dot dot dot, and it just alternates. This is the Taylor series expansion of sine. And cosine is just the same, but this time swap the signs, I believe. If I'm wrong here, you guys can correct me on this. So that's one important use of polynomials to approximate functions. Now, how does polynomials apply to our study? Well, okay, so let's say I have my O cross P from position theory. So I have my O cross P space. So that means every quantity in P can be described as a function, or every element of O can be described as a function of P. So if we want to describe, let's say that this is an O cross P interval for one person for now, and so our P is our position, I believe, or inclination, and O is our dynamic. We want to describe how submissive or dominant a person is with respect to their position. We would say that, okay, so at some point in P, let's say that they're dominant. So, or rather, we have some linear graph. So as their position shifts nearly or closer to being a bottom or a switch, I suppose the O starts being positive. So we have some linear graph over here, or it could be some exponential graph here. Or we could say that, well, let's say that this time, another person here, our O cross B this time is some fluctuating graph, some cubic polynomial. And so as it gets closer to P, or as it gets closer to something like a top position, let's say, it fluctuates, let's say that the dynamic fluctuates. Like he starts thinking, oh, I want to be a submissive, and then, oh, I want to be a dominant. This is best told in the language of polynomials over here. Also, let's say again that we have let's say this time that we're talking about our F cross F again. Let's say we're talking about F cross F. When we want to describe one femboy with respect to another femboy or a bunch of other femboys, it's best we use something called an F-Polynomial. And an F-Polynomial, as I said in the beginning of the video, just takes femboys as inputs. And it goes something like phi of F is equal to, well, some function. and it is in the domain or inside F2. Because phi of F is inside, well, one of these guys, and then F, just any F, your Femboy, is part of our first one, and they're both inside the product or Cartesian product of F2. So therefore, they're in two-dimensional space. As I said a while ago, this axis that we made has F and then F here. So we can describe other Femboys with respect to other Femboys as well. So that's done via this F-Polynomial. And so what we did with this F-Polynomial, which I assume to be degree 3. So if a polynomial is at least of degree 3, then it must have some roots on this axis here. So now, what we want to do is make a relation on why I decided to embed this in a torus or an F donut, right? Now we want to consider why we decided to encode something like this inside a torus, or why we decided, or how we came up with the idea of embedding this function or this F-polynomial on a torus or a Femboy donut. Why did we do that? Or how did we do that? How did we come to do that? Well, notice how whenever we take the S of a given, or the S1 of a given axis, what we do when we take the S1 of this F is that it ends up wrapping around itself and becoming a circle. So our origin is anywhere here. So what we do is we take these 2 points at infinity and then just connect them together, topologically speaking. And so what we do is we take these points and then just connect them, and then say, well, how about infinity here is just equal to minus infinity, which is equal to 0. Let's just say that. Or let's say that it stops at some interval here, a minus a, and this one minus b and b. What we want to do now, what we'll do is make a solid shell out of this. Okay, so what we're gonna do is take minus a and then wrap it onto a, or connect it with a, and say that a is equal to minus a. So now we have a circle. This is S1, a flat circle. Now, in order to construct our S2, what we want to do this time is topologically connect minus b and b. So it becomes another S1. B equals minus b. So now we have another S1. Now, you're asking me, oh, how do we construct something two-dimensional out of this? Well, we just take the product between these two. So take the product of S1 and then another S1. So that we have an S2. And now, imagine a polynomial being encoded onto here. So this is some degree 3 polynomial that crosses the axis about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times. So it has 10 roots. Let's say it has 10 roots. It could be some quintic or quartic polynomial or F-polynomial. And so what happens is that it ends up being wrapped here, and then somewhere here. It's somehow shown here. As you can see, it kind of crosses. It kind of crosses 0 here. So this is 0, and then the opposite of here is 0, the origin. So it crosses here, and then stop, because it's mostly the domain is next here. So it also crosses here. So it goes like this. 1, 2, 3, 4, 5, 6, 7, 8, add more. 9, 10. So there. This is what it looks like when we embed, or when we try to construct an S2 or a sphere with an embedded F-polynomial. So now, what we do is we take another copy of this, so we make another one, make another axis, and then we apply the same procedure again. So A, and then minus A. B, and then minus B. And then we have the same F-polynomial, which is I'll call phi of F. Okay, phi of F. then we have another one, same thing, 2, 3, 4, 5, 6. Yeah. And then what we do, it's just the same thing, even though it looks kind of stretched here, or scaled by a constant, say function. So we just do the same procedure. We make it such that we connect minus a and plus a, wrap it onto itself to get the same thing here, and then wrap b such that it connects with minus b, and then we get this one here, where it's embedded onto this here, and it still crosses that circle. And so, okay, so now we have two copies of itself. So we have two S2s here, and since it is some, it is some axis that takes Femboys as output, we must write here F. And that's what distinguishes it, or these things, from regular polynomials in mathematics. Because we're taking Femboys as inputs and outputs. So now we have these two FS2s. Now what we do next, or to complete the construction of the torus with an embedded function or F-Polynomial, is just take the product of these two. And then there we have ourselves a shape that is isomorphic or homeomorphic to R space. And to show that this is homeomorphic to R space, we just need to show that this is homeomorphic to n. So we have some function that maps this cleanly onto n, the natural numbers. And since n is a subset of R, then I suppose we are already mapping this onto subset of R. Since it's homeomorphic to subsets of R, it is immediately a manifold. And the best way of describing this, since it's S2 in fact, is T2, a torus, or a surface torus, not flat torus like T1. So, since our F-polynomial is embedded in these two spheres, and then we take their product, their Cartesian product, then we have an F-polynomial that is embedded in a torus, or our Femboy Donut. And there it is, there you have it. Why we decided to embed these things? It's because when we try to construct circles, or when we try to construct algebraic structures from these, like torus of course, we end up wrapping this, right? And then wrapping this into itself. Another way to interpret this is we make it into a cylinder. So we take one space only, 1, 2 space, and then let's say we just have this space here. We have this space here only, or just this space here. Still, the thing still crosses 10 times, or still has 10 roots on it. Morning, miss. So what we do this time is we wrap this entire line here, over here, onto itself. So these lines here, which is, well, y or x equals a, what we do is we connect these to make a cylinder. So we now have a cylinder over here. And then we have this, a, and then equals minus a. So in the same process of making this a cylinder, we end up connecting a and minus a. And so b and minus b stay separately. And so, yeah, this is the process of constructing a cylinder out of it. And I believe it's something like taking its quotient with the complex number. So if we construct some complex system, so C, but with F here, or rather F with the C, or Fi, so we call it the cherobic integers, Fi, the cherobic integers, and then take its quotient group with just regular C, the complex numbers, but this time it's something of F here, because we have F as input, so it's all the sets of, well, imaginary integers, imaginary vectors as I like to call them. F plus, well, Fi, well, this is the real component, this is the imaginary component. So all Z, that's like this, such that Fr and Fi are inside our fundamental or underlying Femboy set. And so, to wrap this lesson up, we just take its quotient with CF and then wrap this into a torus. And since this is embedded here, it's embedded in the torus. So that's another way of interpreting this, and that's why we want to construct something like this, so that we're able to sort of get another interpretation of embedding an F-polynomial on a F-donut or F-manifold, 2F2, 2FT2.